We are continuing in 6.1. This is solids of revolution, and we're going to revolve this time around the y-axis. So suppose you have two functions in terms of a different variable. It could look like that. So you could have x equal to g of y, and then x equal to f of y. So you're just switching the variables like that. And then we're going to take this region that goes from C to D. We're going to take all of this, and we're going to revolve it about the y-axis like that. So the region in question, let's go ahead and fill that in again. It's going to look like this. Let me see what size that is. Let's make it a little smaller. It's going to be like so, and then we have these dots like that. So this, usually we use C to D. And we're going to take that region here and revolve it. Okay. So you get the idea there. So it's going to look similar to the stuff we just did, but it's the other direction. So we got to see how we want to kind of set it up, how that's going to look. So you partition the other way and you get a delta y. So the representative rectangle is going to look like this, and then your width is delta y instead of delta x. Okay, so it's going to look like that. Okay, and then you're going to take that and you're going to revolve it this way. Okay, so it's kind of hard to draw it, but you get that sort of thing. And then a little wafer. Try to do it as a sketch. Maybe sometimes the sketches actually look a little better because you're kind of filling the details. Although that one didn't look very well, very good. So let's clean it up a little bit. So that's a washer, but it's on its side, right? So you do the same setup as before. You're going to take the large disc and then subtract the smaller one. And then what you get is what's left over is the washer. So we're going to just go straight to the formula. The volume equals the integral. And because we already did this, we're just changing the letters. Go C to D is what you're integrating over, right? So you're integrating from your C, which was down here. I just wrote over it, all the way to your D. And you get the volume of the big washer. So that's pi times, and then the outside radius, here the large one, is of course your f of y. So you say f of y, and then that's squared because it's pi r squared, right? And then times your delta, your thickness, or the height of the cylinder. So that ends up being your dy. So that's the volume of the large one, and then you subtract the small one, which is g of y. So this would be minus the integral from c to d as well, and then it's of course pi times g of y, quantity squared dy. And you can rearrange and simplify that a little bit. So I want you to, when you set this up, I want you to at least go to here, like you know what the large one is minus the small one. We can think of this as a formula, and you can go to it eventually, but when the setup in your mind is what's the most important, not the formula. So you get pi times c to d, so you just factor out pi in each one. And you have the same integration, so you can do one integration of basically the square of those, the difference of the squares. So it's f of y squared minus g of y squared, and then it's just dy. So you never want to think of it as like this is the formula for horizontal. You really need to think of it in terms of, ideally in terms of summing up all these little pieces from C to D, and then you are working through it. Now, you don't have to write it out and substitute in the functions here, But as long as you know this is where the formula is coming from, you're like, okay, then I can go into here and go ahead and just do that algebraically first, and then do your integration. Okay, let's look at an example of this. So this example, so find the volume find the volume by revolving the area, et cetera, et cetera. Here we go. So find the volume by revolving the area defined by y equal to 1/8 x cubed, y equal to 2x around or about the y-axis. So we want to first graph that. It's pretty much always what you do first is you want to graph your region. So let's do that. Graph by region. This is x, this is y. So you have, so 2, 4, and then you're up at, up there. So you basically want to sketch it. So what I did first here is let's actually graph y equals 2x. So y equals 2x is up 1, 2 over 1. So it's going to be kind of steep like that. Okay, and my scale's off. Let me do that again. So up 1, 2 over 1, 1, 2. Okay, and it doesn't really, it's going to be like this. And then, so that's y equals 2x. And then 1/8 x cubed, you can get the intersection. So let's solve for that. So find the intersection. So how do you find the intersection? Set them equal to 0 and solve. So that should be pretty straightforward. And I'm going to end up just saying what those points are, not doing this to scale. I can already tell you right now. Oops. So it's 1/8 x cubed equal to 2x. All right, and you solve for x. Okay, and so when you solve for x, this is a little different than, I mean, you can just assume x is non-zero and divide it out. Or you can solve it. All right, so I'm going to go ahead and multiply by 8. And so you get x cubed equal to 16x. And so you get x cubed minus 16x equal to 0. Factor out an x squared minus 16 equal to 0. So x equals 0 is one solution, which we already know that down here. And then you're going to get a real and imaginary part. Well, I'm sorry, no, you're not. You're plus or minus 4. So x is equal to plus or minus 4. So when x is equal to 4, what is y? Y is equal to 2 times 4, which is 8. So 4, 8. So let's just call maybe this 4, 8. Let me move this up. And yes, you want to take your time when you do these questions because it helps you think through the details of it. We're going to have to do that again. So 4, and let's just call that 8 right there. So here's 8. And then we know the basic graph of the cubic does that. So that's the intersection we're talking about right here. All this. So this is being revolved about the axis, the y-axis. So that's your intersection is 4, 8. And and I may not do it to scale. I don't really care. I just need to know the basic shape of that. All right. So then x is 4, y is 8. So now when you go this direction, that's your delta y. And then you're going to revolve this way. Okay, so we are revolving like this. Right, so that's what you end up getting. Here's your side view. And so when you go around the y-axis, you need to solve these for x. So we get y equal to 1/8 x cubed. So when you solve that for x, you get x equal to it ends up being the cube root of 8y. Well, the cube root of 8 we actually know, so you can say that's if and only if x is 2 cube root of y. Okay, so then now for x, that's just 1/2 y. So in the other case, you have x is 1/2 y. So those are the two functions we're going to be using here and here for your graphs. So the top, so now you need to know the outside and inside. So the outside is x 2 cube root of y, inside is 1/2 y. So that's what you can put in over here. So the large one is 2 cube root of y, and the small one is 1/2 y. All right, so set up, take your time here next, and what would the formula look like? So the volume is outside minus inside. So now you're basically following this, right? We know the outside radius, inside radius, revolving about the y-axis. And frankly, I would go right to this one and then maybe just factor later. I would probably just say it's 0 to 8, right? So you're going from down here. I was going to actually mark that. So you're going from down here, which is 0, to up here, which is 8. So that's your C to D. So 0 to 8. And then it's pi outside squared. So the outside radius is what? It's the 2 cube root of y squared, and then your dy. And then minus 0 to 8 pi 1/2 y squared dy. And then we simplify it. All right, so check that out. I'm not going to use up the rest of the video to simplify it. I do not have an answer to this one. So this could be a setup question. And I'll talk more about that later if we ever do a setup question. But sometimes that's the main point. Like if you're practicing these problems, the rest of that's pretty straightforward integration. I mean, it's not just a polynomial, but it's not too difficult to figure out from there. And I don't have an answer. I'm looking at my notes. So try to work it out, see what you get. And then if you get weird anomalies, then you know something's wrong. Like if you get a negative volume, that wouldn't make sense. If you get something that's, 200 million somethings, that's probably a little big, right? Because we're not talking large numbers here when you're integrating, that kind of stuff. Okay, next we will do an example of another thing in 6.1, which is solids with the known cross-section. That probably will be a short video, and maybe I'll do one more example or I'll solve this for you and I'll probably do another example. Let's just do another example. And we'll do volumes of cross sections or known cross section.